All right, hello. Let me get the music off because it's a little bit distracting. Welcome back. Hope everyone's Thanksgivings were great. I know I certainly enjoyed mine. Having some time off was certainly nice to relax. As you can see by the title of today's video, we're going to be talking about springs for Physics 1. Um, Honestly, not my favorite topic in the world, but very important nonetheless. So let's get into it. We'll talk about it, and then after the lesson, maybe we can chat a bit. But first, we gotta learn, and as you can see, we're talking about springs today. So, let's jump into it. So, before we even get into our slides, let's just think a little bit about like what a spring is. I'm sure most of us uh, have seen a spring or have used a spring before. And it's one of those things that just goes like boing, right? You squish it and then it wants to like expand backwards and send things flying. And actually that's a really good description of what a spring is. And having that understanding will help us a lot in talking about springs. So if you think about like compressing a spring in between your fingers, it doesn't just stay there. Like sure, if you're applying enough force, it'll stay there, but that spring wants to push your fingers back apart, right? It doesn't want to stay pushed together, otherwise it would be in that pushed position. It wants to push you apart. So certainly there's got to be some sort of force associated with springs. And similarly, the if the spring tries to push our fingers apart or tries to push any object apart, that object will gain some sort of velocity. So if something suddenly gains a velocity, there's a force being applied to it, that means there's work being done, which certainly means that there's energy involved. So that's just foreshadowing what we're going to talk about. So let's first talk about force. So this guy named Hooke came up with the spring force equation, and we call it Hooke's law. So what's basically being said here is that there's a force associated with springs, which we denote F sub s, and that's equal to negative kx, a very simple equation, but we have to figure out what these variables are because we haven't really worked with them too much. So k is something we call a spring constant. And as the name suggests, it's a constant value, just any number really, and it differs from spring to spring. So a good way about thinking about the spring constant is about how easy or how difficult it is for the spring to compress. Certain springs require a lot of force, a lot of effort to compress them, whereas other springs, they don't require as much effort. And I guess some good examples are like, we can think about a slinky as a spring, kind of, and that doesn't take a lot of effort to compress. I guess a slinky really isn't a spring, but you can imagine a spring that's similar to a slinky in that it's easy to compress. But then there are other springs, maybe like a spring inside of a pen or a pencil, mechanical pencil, and those require quite a bit of effort to compress. So that's what K is, and usually that's given to you, or we're trying to find that. X is the amount of displacement of the spring. So all of these springs are in some sort of equilibrium position, which is like the place that they're happy at. And that's just like the natural state of the spring. However, when we compress it, or expand it, the spring changes from equilibrium position, and we want to measure that displacement from equilibrium position, and that's x. So let's look at the diagram down here. Interestingly, the force is always in the opposite direction of the direction of displacement. So we can think about when we compress the spring with our fingers, we're pushing downwards, so it's being displaced downwards, but the spring is trying to push your fingers apart. So the force is going upwards, right? If I'm pushing down with my index finger, the spring is trying to push my finger upwards. So it's an opposite direction. So we have just the spring here, which is normal, it's happy how it is, and this yellow dot represents the equilibrium position because that's the furthest point that the spring reaches. But then suddenly, someone applies a force to it, maybe someone pushes it, or an object pushes it or something, and the spring compresses quite a bit. Now, with that compression comes a force pointing in this direction, right? The spring is trying to push that object away from it. It doesn't like being compressed. It wants to go back to its equilibrium position, right? Almost everything likes to be in its equilibrium position. So the force is equal and opposite. But right now, the end point of the spring is at this red dot. So x is defined to be this displacement from the red dot to the yellow dot. So that is what our x value is. And let's just take a look at a simple example here using Hooke's law. So a 1 Newton force is able to displace a spring 0.5 meters from its equilibrium position. Find the spring constant. All right, so, well, what do we know? We know that F is equal to negative kx. That's by Hooke's law. And we should probably define some sort of direction. So perhaps the right is like the positive and to the left is negative, right? Just have that positive and negative sign so we know with the vectors which direction they point, if they should be positive or negative. Okay, we're given 1 Newton, so force is equal to 1 Newton, but in this case, it's pointing to the left, so we need to make that a negative 1 Newton. Okay? And then x we're also given 0.5 meters, right? That is its displacement from equilibrium. It displaces the spring 0.5 meters from its equilibrium position. And with this diagram, we see that, okay, this yellow is probably the equilibrium position, but now we've compressed the spring and now it's here, so this distance is 0.5 meters. So then we can just solve for k. If we do a little bit of rearrangement, we get k is equal to negative f over x, and then we can just substitute in what we have. Negative force is negative 1, x is 0.5, so k is equal to 2. But we should have units on this. Units are very important. So if force is in meters, or sorry, not in meters, in newtons, and x is in meters, and we're dividing the two, then the units for k are newtons per meter, right? Newtons over meters, I'll just say newtons per meter. So that would be our value for k. So that's just a simple example getting us used to using Hooke's law. Okay, so now there's energy associated with it, with the spring, which is something I alluded to in the beginning. If an object is pressed against a spring, that's how it starts out. The spring is compressed. It wants to go back to its equilibrium position. So it's going to expand back out to equilibrium, but it's going to send this object flying. So let's just say I have a wall here, and then a spring, and then an object, which is not attached to the spring, it's just pushed against it. The spring wants to go to its equilibrium position, somewhere here, but that's going to send the block flying in this direction, because the force of the spring is this way. So this block gets some velocity, which means that work is done. So that means there is energy involved, right? And certainly we can think about it. When the spring is all smushed up, it has potential to send this object flying. Potential, that's the key word there. And all of this energy is stored up in here, and then when it gets to this equilibrium position, it doesn't have that potential to move an object anymore because it's in equilibrium position. So all of that energy which was stored up in here gets sent to the block, and that just makes the block go flying that way. So let's take a look at the energy, and in fact this is called spring potential energy. So that should make sense from this diagram here, where the spring, when it was compressed, it had potential to send this object flying. That's not actually where the word potential comes from. But yeah, hopefully that's a good reminder that it's called spring potential energy. And that can be especially confusing when we look at the formula. So we have U, which is the symbol for potential energy, sub S. So subscript S is used to denote springs. This is equal to 1/2 kx squared. And that's why I said it's a little bit confusing. Because although this is potential energy, this equation looks eerily similar to kinetic energy. Remember, kinetic energy was equal to 1/2 mv squared. So these two equations are very similar to each other, but they mean different things. So I'm actually going to get rid of this kinetic energy because I don't want it to be confusing. So this is saying the spring potential energy is equal to 1/2 k, which is the spring constant, which is what we defined earlier, times x squared. And lucky us, x is still the same definition as in Hooke's law, where it's the amount of displacement of the spring. So if we have this graph here, where we're graphing the force, the spring force, by the displacement, so displacement is on the x-axis and the spring force is on the y-axis, we have this straight line here. And the first thing we should be asking ourselves is that, does this make sense? And well, if we go back to Hooke's law here, this is what we're graphing on the y-axis, this is what we have on the x-axis, and this quantity x is being multiplied by this negative k, and that's just a constant. So if we have, suppose f of s is y, and this is just some constant k, and then x, then we have y equals kx, which we expect to be a straight line. So the shape of this line, or the shape of the graph is encouraging because it's a straight line. We don't really need to worry about what exactly its slope is or where, well, I guess it does always intersect at the origin. But the point is that our graph is a line, right? So suppose we want to take the area under the curve at some point here. So I'll just label this like x naught. Let's just do that for fun. And we see that we have a triangle that's formed. So the area of a triangle is 1/2 base times height. So we have 1/2 x, I guess I'll change it to x naught now, x naught times f of s, right? So we're at some point here, which is just some spring force. I'll just leave it as f of s. And then that's equal to 1/2 x naught times k of x, because that is what f sub s is. And if we do that multiplication, we get 1/2 kx squared. So it might be a little bit confusing why we decided to do the area under the curve, but the reason for why we do this has a little bit to do with calculus, which we don't really touch with here. However, the skill of being able to see this graph, force versus displacement, and determining the energy from it is important to have. So if you see this force versus displacement graph for springs, to get the energy, you take the area under the curve. And that's what is said here. The area under a force versus displacement graph gives the work, which equals the potential energy for springs. All right, so we've seen force and we've seen a little bit about energy, but maybe you're starting to think, what about conservation of energy? Right, we studied conservation of energy the last 2 weeks and we had some equations for that, but now there's a new form of energy and we haven't really taken that into account when we do conservation of energy. Well, just like when we introduced like non-conservative forces, work with the non-conservative forces, we added a new term to our conservation of energy equation. We're going to do the same thing here. So with conservation of energy, we say initial energy equals final energy. And then this equation here, without the red terms, let me actually just get rid of these. This is what we saw previously. This is what we're used to. The initial kinetic energy plus initial potential energy plus work non-conservative equals the sum of the final energies. But now we're introducing a new type of energy. So the energy here, that's just the sum of its individual parts. So we have multiple different types of energy that compose this. So we just take the sum of them. So we just introduce these terms back into the equation. So now we have a supermassive equation for conservation of energy, and it'll be the one that we want to go to whenever we want to do a conservation of energy problem. Okay, I think with that said, we're ready to attack some problems. So we'll start out with some graph questions, which are very important to be good at, because these come up a lot on exams. So a block oscillates without friction on the end of a spring as shown. The minimum and maximum lengths of the spring as it oscillates are respectively x min and x max. So that's seen here and here. The graphs below can represent quantities associated with the oscillation as functions of the length x of the spring. Okay, so the first part is asking which graph can represent the total mechanical energy of the block spring system as a function of x. So mechanical energy, that's just equal to, that's just saying E, what we call E, and that's the sum of kinetic energy plus potential energy plus spring potential energy. Well, okay, let's see. We're given that the block oscillates without friction. So suppose we wanted to consider the change in energy from x max to x min, right? This block goes here, and then there, and then there, and then there, like it's oscillating back and forth like that. But let's consider we start at x max and we go to x min. Well, in order to do that, we can use conservation of energy. We can say that energy at x min is equal to the energy at x max. And similarly, it doesn't really matter where we are within these bounds here, because that's only where the block is. The block never goes outside of these bounds. No matter where we are in here, the energy will always be the same as one of these x min or x max. So throughout its oscillation, the energy never changes. And that's mostly due to no friction being present, which means there's no non-conservative forces being applied. So if we think about this here, we get KE initial plus U initial plus U spring initial plus work non-conservative is equal to KE final. I guess I should add this work non-conservative plus there. Right, so that's our conservation of energy equation. And we say, okay, this work non-conservative term, that goes to 0. So we're left with this initial sum of energies is that initial sum of energies. So we have E initial equals E final. So no matter where we are in there, within this region, the energy will be the same. So that means answer choice D would be our best option. Okay, wonderful. So now we want to know which graph can represent the kinetic energy of the block as a function of x. All right, well, the first thing I would do is write down my equation for kinetic energy, which is 1/2 mv squared. And so the thing that we want to monitor is, well, 1/2 and m, those are both constants, so that's not really going to tell us too much. The velocity is the important piece of information. So if we consider its oscillation, when the block is at x max, the velocity of the block will be 0. The block momentarily stops at x max because it's changing directions from going to the right to going to the left. Similarly, at x min, the block changes directions from going from the left to going to the right. And when we have that change of directions occurring, that means the velocity is momentarily 0. So that means at x min and x max, velocity is 0, which means kinetic energy should be 0. So just with that information, we can start to look at these graphs given, and we take a look at A, and we see, okay, at x min, we're up here, which is not 0. So we can eliminate choice A. We take a look at B, we see that, okay, at x min and x max, we're at 0, so that's good. It's possible. C, same thing, both at 0, so that's good. D, we're not at 0, we're somewhere up here, so it can't be D either. So we're in between B and C. And now choosing the answer for this can be a little bit difficult. And we won't worry about it too much now. We'll go through it more thoroughly in a future lesson. But our answer is going to be C here. And there's a couple of ways to think about it intuitively. Choice B is saying as we go, along our path from x min to x max, what are we looking at? The kinetic energy increases linearly. And for C, it's not saying that the kinetic energy increases linearly. This looks more of like a quadratic function. Let's go to B. If it were to increase linearly, then this mv squared, this v squared term would have to be this v term would have to be a square root function, so that way the square root and the squared would cancel and we would be left with a linear function. But the velocity isn't really a square root of this distance traveled necessarily. So it's better to think about it like we have this 1/2 mv squared that looks kind of quadratic, and this graph here looks kind of quadratic. It's not the best way of thinking about it, and as I said, in a future lesson we'll explore this more thoroughly. But for now, the main exercise was seeing that, okay, we can already eliminate choices A and D. So yeah, that's our first question. Let's move on to the next question. And this one's a little bit more interesting. Now we're going to actually work with the springs and use equations. So a block of mass 3 kilograms is hung from a spring, causing it to stretch 12 centimeters, as shown. I'm going to highlight that because that says centimeters. The 3 kilogram block is then replaced by a 4 kilogram block, and the new block is released from the position shown at which the spring is unstretched. How far will the 4 kilogram block fall before its direction is reversed? Okay, so let's handle the first situation first, which is with the 3 kilogram block, and then we'll worry about this 4 kilogram situation later. That just seems a little bit further away, that we don't need to worry about it. Okay, so let's zoom in on this block. The 3 kilogram block, let's think about what forces are being applied to it. Well, if the spring is being suspended vertically and the block is just hanging there, it should have this force due to gravity pointing downwards, right? That's always there. We're used to seeing that. But now we have this spring, so there is an associated spring force, and we should remember that the spring force points opposite the opposite direction of the displacement. So we went from here downwards, that's the displacement, so the force should point upwards. And this makes sense, right? The spring wants to go back to its equilibrium position like this, so the way it's going to get back to equilibrium position is by pulling itself upwards. So we have the spring force pointing upwards. And are there any other forces? Well, there's no normal force because it's not on the surface. There's no frictional force, nothing else. So that's sort of our free body diagram. Okay. So the block is sort of just, sitting there. It's reached this position here where the spring is outstretched. So that means at this point, the block is not accelerating. So we can sum the forces in the y direction, and that should equal m times ay, and that's going to be 0 because there's no acceleration in the y direction. Okay, so now we sum the forces and we get Fs minus Fg equals 0. Okay? And then we can do some rearrangement. Fg equals Fs, and we have equations for both of these. So mg equals negative kx. All right? So what are we trying to solve for here is really the question. Right now we've sort of just drawn a free body diagram and thrown it into an equation. Well, we have the mass that's given to us, that's 3 kilograms. We have gravity, which is good. Do we have x or k? I don't see anything about the spring constant, so we don't have k. But we do have x, because we know it's been displaced 12 centimeters from equilibrium. So that means we can solve for k. So we'll get k is equal to mg over negative x, and by substitution we'll get this is equal to 3 times 9.8 divided by this, and when we do this division we get 245 newtons per meters. So that is just the spring constant that we found. Move this here. And that's going to be helpful because we want to see how far will this 4 kilogram block fall before its direction is reversed. Surely we're going to need this value for k. The spring isn't changed, so in this new situation here, the value for k will still be the same, 245. So it's good that we found that. So now we have to figure out what happens with the 4 kilogram block. So I'm going to redraw the picture here, and you're going to have to excuse my horrible art skills. So we have like the ceiling here. We have the spring, and this is 4 kilograms. That's its initial position. And then like we let it drop, and then the spring stretches out until we get down here. And that's where the block is changing its directions. Okay, well, how exactly are we going to do this? When we're here, what can we say? Well, the block is temporarily stopped, which is fine, but we're trying to solve for this distance here. I think we can probably use conservation of energy. And in order to do that, we have to define our h equals 0 line. So I'm just going to do it here because this just seems like a good place to do it since everything else is occurring at h equals 0 or above it. And we're trying to find this distance here, which we'll just call h. Okay, so what is our conservation of energy equation? We have E initial plus work non-conservative equals E final. So we have kinetic energy initial plus potential energy initial plus spring potential energy initial plus non-conservative work equals kinetic energy final plus potential energy final plus spring potential energy final. Okay, so going through here, let's try to see if there are any terms we can eliminate. So initially, the spring is unstretched. We can see that here, and are we given that? I don't know. I mean, it's kind of implied that it's like hung from a spring, like the 3 kilogram block is hung from a spring, and then it's stretched from equilibrium, and then we replace it with a 4 kilogram block. I don't know, it's kind of implied, but I guess maybe not. So if the spring is initially unstretched, that means there's no displacement from equilibrium, so there's no spring potential energy. So we can get rid of this term. And similarly, there's no kinetic energy since the block starts from rest. So we can get rid of that as well. And then also we can consider, are there any non-conservative forces that are going to be acting on the block as it falls down here? And not really. The only forces present are gravity and the spring force, and neither of those are non-conservative. So we don't have any of these terms to worry about, so we can get rid of that. So now we'll analyze its final position. So this is the point where the block, we're asked to find the point where the block momentarily stops or where it changes its direction. I guess it's like the opposite, where we're asked to find the point where it changes direction, which is where it momentarily stops. So if it momentarily stops, there's no kinetic energy at that point. And similarly, we defined h equals 0 to be this point where the block stops. So if h equals 0 at that point, then there's no potential energy, because when we have u equals mgh, that's just going to go to 0. And then spring potential energy, surely there is, because now the spring is displaced from its equilibrium position. So there is that potential energy. It's trying to make this block move. So there will be that energy. So we have u, whoa, that's not a pen. We have u initial equals u spring final. So we've simplified the equation quite a bit, and we can do a substitution. We get mgh equals 1/2 k x squared. And what are we trying to solve for here? Well, h would be an interesting quantity to solve for, because that is kind of what we defined our quantity to be, right? We said that this 4 kilogram block was a distance h from h equals 0, and we want to find the distance from its initial point to the point where it changes. So h would be an interesting thing to account for. But then what's x? Right? Like, it's an interesting question, because what's x defined to be? It's like displacement from its equilibrium position. But if up here the spring was in equilibrium, and here we're not in equilibrium, then surely x is that displacement, which would be the distance from here to here. But that's what we defined h to be. So really, x and h are the same in this case. This is not always true. This kind of is due to the fact of how we defined h equals 0, and also just due to the problem in general. So this is not always true, but we can see that x and h are the same, so we can substitute this x with an h, and then solve for h. So I need some room, so I'll just bring it over here. We get mgh is equal to 1/2 kh squared. And we're solving for h, so we can cancel 1h on both sides. So that goes away, that goes away. And we're left with mg equals 1/2 kh. And then if we solve for h, we get h is equal to 2mg over k. And we have all of these quantities. We have the mass is now 4 kilograms. G is our usual 9.8. And k we solved for before. We got that to be 245 newtons per meters. So we can solve for this. This is equal to 2 times 4 times 9.8. All of this divided by 245, and that will be equal to 0.32 meters or 32 centimeters. And, well, it's a multiple choice question, so out of these options, we would go with choice C. So it's helpful to take a moment to pause to think, does this answer make sense conceptually? So we have the spring here in equilibrium position, and when we put a 3 kilogram block, it displaced 12 centimeters. So when we put a heavier block, certainly we would expect it to displace more than 12 centimeters, because this is heavier. It's applying more of a force. The force due to gravity is stronger. So the answer we get should be greater than 12 centimeters. And indeed, we did get an answer greater than 12, 32 centimeters. Unfortunately, all of these answers were greater than 12, so we couldn't eliminate any of them. But before we started the problem, if we made this realization that our answer should be greater than 12, then it could have been possible to eliminate some of these answers, but in this case we couldn't. So it's greater than 12, which is good. 32 centimeters, sure, that seems reasonable. So the answer somewhat matches intuition, which is always good, because yeah, it's good to get a good sense of what physics in the real world looks like. Beautiful. Let's keep chugging along to move on to another question. So a block of mass m on a horizontal surface is connected to the end of a massless spring of spring constant k. The block is pulled a distance x from equilibrium, and when released from rest, the block moves towards equilibrium. What coefficient of friction between the surface and the block would allow the block to return to equilibrium and stop? Alright, so this is quite interesting. We're trying to find the coefficient of friction. So mu is equal to some value which we're going to try to solve for. That's a pretty bad question mark. That's, how do you draw a question mark? There we go. Okay, so we're trying to solve for mu. And we start at some initial position here, which is x away from equilibrium. And where do we want to end? We want the block to return to equilibrium and stop. So our final position should be at this dotted line. So let's just mark it. This is final position, and this is initial. Let me just move the star. There. Okay. So what do we think we can use to do this? Well, we've seen a lot of questions recently about comparing an initial position to a final position. So we can use conservation of energy, right? I mean, we have an initial position, final position. Conservation of energy seems like it would work, but we should probably define an h equals 0 line first. And h equals 0 can be kind of confusing. When we see a problem like this, we might be tempted to do something like, okay, let me define this to be h equals 0. And perhaps, unfortunately, we can't always do this. In fact, we can basically never do this, because h equals 0 is a horizontal imaginary line. If we think about what h equals 0 is, that's mainly used for our potential energy, our gravitational potential energy. And that's the vertical distance from our baseline. So we can't really do this vertical h equals 0 because we have no way of calculating gravitational potential energy from this. So we have to define it to be a horizontal line. And it might look a little bit weird, but I'm just going to say this is h equals 0. And yeah, it kind of looks weird, but the good thing about it is that we know that this block, it just moves from here to here. It just goes like that. It doesn't go like this. It doesn't fly up in the air and then come back down. It's not like going on some random path upwards and away. It's always at this h equals 0, and then more importantly, it starts and finishes at an h equals 0. So that just means we won't have to worry about gravitational potential energy. But to see it in action, let's actually write out the equation and see what happens. I'm not feeling red, I'm feeling blue. So initial energy plus work non-conservative equals energy final. So if we write this out, we get KE initial plus U initial plus US initial plus work non-conservative equals KE final plus U final plus US final. So now we need to figure out, do any of these quantities go to 0? Okay. So let's see. The block is pulled a distance x from equilibrium, and when released from rest, the block moves towards equilibrium. So initially, the block is at rest, which means its velocity is 0. That means there will be no initial kinetic energy. Because velocity is 0. Okay. There's also no potential energy because the block is at h equals 0, so we just don't have to worry about that. Is there spring potential energy? And the question that you should be asking yourself, that your follow-up question to get the answer should be, well, are we displaced from equilibrium? Because that's what provides the potential energy. And certainly we are. We can tell from the diagram, and the question tells us that it's pulled a distance x from equilibrium. So this spring potential energy is not 0. There is some quantity there. Non-conservative forces, are there any present? Yes. We're trying to find the coefficient of friction, so certainly there's a frictional force there, so we kind of need that WNC term to be there, otherwise we can't solve for mu whatsoever. Okay, so that's the left-hand side. Let's look at the right-hand side. Can we get rid of any of those? So at its final position, what's going on? Let's read the question. What coefficient of kinetic friction between the surface and the block would allow the block to return to equilibrium and stop? So we want it to stop at its final position, which means the final kinetic energy should also be 0. It should have a 0 velocity there. What about potential energy? Well, at the final position, we're still at h equals 0, so that also goes to 0. What about spring potential energy finally? Well, if we're at the equilibrium position, we're not displaced from it. That value of x will be equal to 0. So that means there's no spring potential energy either. So that goes to 0, which means we're left with US0 plus work non-conservative equals 0. And this might seem okay to some, and to others might be a little perplexing. Let's take a moment to pause and understand what's going on conceptually once again. So we started from this equation, we expanded it out, and then we contracted it back here. And we see that this non-conservative work stayed throughout. So this is saying at the initial position, the initial energy is just equal to the spring potential energy. And at the final position, the energy is equal to 0. So all of this energy, which was present at the beginning, has gone away. It's gone to 0. So where did all that energy go? That energy is dissipated by our non-conservative forces. So that's why we have this non-conservative work term here, because it's separate from this energy. It takes this energy away. And then that's why we have 0 final energy. Okay, so that's just kind of understanding what this equation is, but now we have to use this equation to solve for mu. That's kind of what we're looking for. So the initial spring potential energy by equation, that's equal to 1/2 kx squared. And then non-conservative work, well, what are the non-conservative forces? Let's kind of draw a free body diagram for that. So let's just go over here. We have the block. What are the forces acting on it? We have F sub g pointing downwards. We have the normal force pointing upwards because we're on a surface. And now the spring force, we should be aware that that exists because there's a spring involved. And friction, we should also be aware that exists. But friction kind of depends on the direction of motion. So from the picture, it's kind of clear that the block will move from here to here, so it moves to the left. And let's think, does that make sense? Well, if this dotted line is the equilibrium position, and we pull the block this way, then we want to go back to equilibrium, so the force should be pulling us this way. That's what the spring should be doing. So the spring force should be to the left. So let's draw that in. I'll call it F sub s, and friction opposes motion, so that's going to go to the right. Okay, So we have our free body diagram. There's no other non-conservative forces, so friction's the only one to worry about. So this is going to be equal to Ff times the distance times cosine of theta, and we're saying that's equal to 0. Well, okay, I know that by formula, F sub f is equal to mu times F sub n times cosine of theta. Alright, so we're getting closer, but now we have this F sub n term here, and we can obtain that by looking at our free body diagram. Fn is pointing in the y direction, so what happens if we sum our forces in the y direction? Well, we get Fn minus Fg, but this should be equal to m times the acceleration in that y direction. And as I said before, this block is not flying upwards and coming back down. It's just moving towards the left. So it's not moving in this upwards direction. So certainly, there's no acceleration in that direction for the system. So this goes to 0, which means that Fn equals Fg, which equals mg. Great. So we can make this substitution back in here. Let me go back to blue. We get 1/2 kx squared plus mu mg times d cosine of theta. Let's try if we can figure out what d and cosine of theta are. So d is the distance that's traveled of which the force is being applied for. So if we start here and we end here, then that value for d is just the change in these starred positions, which is simply x. So d is equal to x. And then cosine of theta, well, that theta is the, let's just go here. Theta is the angle between force and direction of motion. Well, we said that friction always opposes the direction of motion, so theta is equal to 180 degrees. So that means cosine of theta equals cosine of 180 degrees, which is equal to -1. So we'll substitute a -1 in here, and that should equal 0. And now we just have to solve for mu. So we get 1/2 kx squared minus mu mgx. So this -1, I'm just, changing this plus sign to a minus sign. This equals 0. 1/2 kx squared equals mu mgx. So just adding this term on both sides. And now we can divide by this mgx on both sides. We get mu is equal to kx squared over 2 mgx. So I sort of just broke this 1/2, or I combined this into one fraction. This right here is equal to kx squared over 2. And then we're dividing by this mgx, so we throw that in the denominator as well. And then we should see that one of these x terms cancels. So we're left with kx over 2mg. And if we take a look at some of our answer choices, we see that choice C is our answer. Okay, and then are there any qualitative observations we can make? Well, kind of. The coefficient of friction, it depends directly on the spring constant and the distance it needs to travel, and then indirectly to both mass and gravity. So some sort of qualitative assessments we can make, but nothing too exciting. But yeah, that's our answer for this question. Wonderful. So yeah, let's move on to the next question, and we can take a moment to read it. I'm going to hydrate. Okay. So I remember when I was taking physics, this kind of question was like not my favorite type of question. I never looked forward to this, but it's important to learn how to solve these questions. So we have a 5 kilogram block suspended from a spring with spring constant 3 newtons per meters in an elevator. Elevator is accelerating upward at a rate of 1 meter per second squared. What is the spring's displacement from equilibrium? Okay, so we know that this is 5 kilograms. So let's just write that. We have mass is equal to 5 kilograms. We're given that the spring constant K is equal to 3 newtons per meter. And the acceleration is equal to 1.0 meters per second squared. All right. So what are we going to do from this? We want the displacement from equilibrium. So this displacement, which we'll just call delta x, that's going to be equal to some final position, which we'll try to solve for, minus the equilibrium position. Right? So just given the equilibrium position and the final position, we can obtain that displacement just by, taking the difference. So how can we find this equilibrium position? When is the system in equilibrium? That's a really good starting question to ask yourself. And the answer to that is when the elevator is not accelerating. You can just imagine the spring mass system in just a room. It's just being hung there. It's going to be in equilibrium position. Keep in mind, we're talking about the system, not just the spring itself. But the entire system will be in equilibrium. This block will just be stationary. It might like bobble up and down and then eventually steady out to be at a stationary position. But if this elevator was not accelerating, then we would be in equilibrium. So let's consider when not accelerating. Let's consider what does the free body diagram look like, and we'll look at the block in particular. Well, we have Fg pointing downwards, and we have some spring force pulling it upward, or trying to pull it upward. Right? The block causes the spring to change from its equilibrium position. Perhaps the spring without the mass looks something like this, but now we've pulled it down due to the mass of this block. So there's that spring force trying to pull it back upwards, and there's no acceleration, right? We said it's not accelerating. So if we take the sum of the forces in the y direction, which is equal to m times ay, that should equal 0, because this acceleration term is 0. Okay, so let's take the sum. We get fs, because it's pointing upwards, and we subtract fg, because it's pointing downwards. That should equal 0. Wonderful. So we can do some substitution here. We get like k, x, I'll just put an x initial, or rather, let me put x like equilibrium. Xeq minus mg is equal to 0. And we're trying to solve for this xeq, right? We want to put it in here eventually, once we get x final. So we can solve for xeq. But first we'll say k xeq equals mg. So xeq equals mg over k. And we're given values for mg and k. We noted them here, m and k, and g, we know that to be the gravitational constant. So this is going to be equal to 5 times 9.8 divided by 3. So that's going to be equal to 16.33 meters. Okay. What does this exactly mean, though? 16.33 meters, it's a number, but from what? And really, it comes back to the example that I pointed out, without the block, the spring looks something like this, but with the block, it's displaced by this much. So this is going to be 16.33. Okay? So then when the when the elevator is accelerating upwards, this block may either go further down or upwards or something like that, but we're going to get like another distance here, and then we're going to try to find the distance in between these. Like this pink value is really what we're trying to solve for, this delta x. But this is what the 16.33 is. It's the change from the equilibrium position of the spring. Okay? So now let's try to consider what happens when the elevator is accelerating. I'm just going to move this over here. When accelerating. All right, so let's do another free body diagram. We have Fg pointing downwards. We have the spring force pointing upwards. Are there any other forces to consider? No, not really. So we can take the sum of the forces again. That's going to be equal to MAY. But now, this is not equal to 0 like we said up here. Because up here, we said that the elevator was not accelerating. We were at rest. But here we know that the elevator is accelerating with this 1 meter per second squared. So we can't set this equal to 0, but let's still go through the procedure we went through before, where we said Fs minus Fg equals MAY. So that means 1/2 K x, I'll put like x sub f to denote final. No, sorry, that's not right. I was thinking energy. We want kx sub f. Kx sub f minus mg equals may. I'll just zoom in here. So kxf equals may plus mg. And we're solving for xf, right? Because we want to go back here and plug it in there. So this gives us x sub f is equal to may plus mg, all of this over k, and now we can solve for it. M is, I believe it's 5, yeah, it's 5. Acceleration is 1.0 plus 5 times 9.8, all of this divided by k, which we're given to be 3. And when we do this, we get x sub f is equal to 18 meters. So if we go back to here, when the block is accelerating, or when the elevator is accelerating, the block actually is kind of lower down than if the elevator was not accelerating. So that would be this vertical distance here, which is what we were trying to solve for, and it happens that that is 18. So if we come back to this equation, the displacement from equilibrium is this displacement right here. Because at this point, we said that the system was in equilibrium. But then when the elevator accelerates, the block drops down here, so we want that vertical distance. So this would tell us that delta x is equal to xf minus xeq. That's going to be equal to 18 minus 16.33, which is equal to 1.67 meters. And that's our answer. So quite an interesting question here, and I think the tricky part is actually the first step, to consider what happens when the block, or when the system is not accelerating. But this is a very helpful first step and something you always want to consider when we're doing spring problems. If the system or the capsule that the system is in is accelerating, take a moment to pause to consider, what if we're not accelerating? What does the system look like? Are we in equilibrium, or is the system in equilibrium? So that's that critical first step. And then from there, we can consider our final position. What happens when the system is accelerating. Great. So yeah, neat question there. Now we'll move on to a question that I kind of enjoy, although it might look kind of nasty. And it's one of these like roller coaster type things where we have like a block rolling down a hill or something. But anyways, from the diagram, I didn't really write out the question. It's kind of intuitive. But we start out from this point A, and this block is going to slide down here, slide down, hit the spring, and then it's just going to end up here with the spring compressed. And we just want to know, how much does the spring compress? To some people, this question might seem like such a simple question, like, well, why are we doing it? And the question of why we're doing it is hard for me to answer, but maybe to the curious few, you're like, wow, we can actually solve for this, and we are going to solve for it. But let's take a moment to look at our toolkit here of information that we're given. The surface is frictionless except for the section from B to C. All right, so that gives us an idea that if we decide to do conservation of energy, which seems like the most plausible way to approach this problem, considering I don't really know any other technique to do it, when we consider non-conservative forces, B to C, there definitely will be a non-conservative force, but from A to B, perhaps there won't be any, because there's no friction. Similarly, from C afterwards, there's no friction, so that's a good symbol, or a good sign. The distance from B to C is 1 meter with a mu equals 0.25. So this, I'll just call it x, and that's equal to, x is equal to 1 meter, and mu is equal to 0.25. I'm just going to add a page because I feel like I will need it. All right. The block is 2 kilograms, so mass equals 2 kilograms. The vertical height from A to B is 5 meters, so let's draw that. This is 5 meters. And the spring has spring constant K equals 10 newtons per meter. Okay, with all of that said, I think we're ready to start this. And it really does seem like we're going to need to use conservation of energy. So the problem helped us out a little bit in that it denoted points A, B, and C to like break up the conservation of energy problem. But if it wasn't given to us, then this is something we would want to do. And the easiest way to do this is consider, when do things really change? So we should probably label the starting point, so we'll give it an A. But then as the block is sliding down, there's nothing too significant changing until we hit B. When we reach this flat surface, which is one change, but also we reach this rough patch where there's friction. So that's why we put B here. And then, the block is sliding along here. It's pretty flat, but then we end this frictionless patch. So we put C here. And then afterwards, well, we hit the spring, and, that all happens after C. So that's how we would come up with those points. So let's consider what happens from A to B first. And we'll use conservation of energy. So E initial plus work non-conservative equals E final. And we'll use our massive equation. Work non-conservative equals kinetic energy final plus U final plus U spring final. And now comes my favorite part, which is determining which quantities go to 0. But even before that, if we're doing conservation of energy, we have to define what our H equals 0 line is. And, well, this surface here is flat, and everything kind of occurs on or above that surface. So, at least for me, I'm just going to define this to be my H equals 0 line. Great. So with that said, let's consider what quantities go to 0. And maybe I'll just put subscript A as well. This should be US initial A. Work non-conservative, and then on the right I'll put B's, just to signify that we go from A to B. But it's kind of understood since I wrote A to B at the top. Okay, so the block starts from rest. I don't think it's given to us, but we'll just assume that. It starts from rest up here. So that means there's no kinetic energy initially. So we will make that go to 0, something like that. Is there potential energy? Yes, we're not at h equals 0, so that's a non-zero quantity. Is there spring potential energy? No, because there's just no spring involved from A to B, so we don't have to worry about any potential energy of the spring initially. Are there any non-conservative forces? No. We know that there's no friction that was given to us. It's a frictionless surface from A to B, and there's no other non-conservative forces to worry about. The only other forces are really gravity and the normal force, but neither of those are non-conservative, so that goes to 0. Wonderful. Let's consider what happens when we're at B now. Is the block, does it have some sort of velocity? Like, does the block have kinetic energy? It should, right? It's falling down this hill. It goes from 0 velocity to hopefully some velocity. So yeah, I expect this to be non-zero. Is there any final potential energy? No. We're at the h equals 0 line here, so this will be 0. And then, is there any spring potential energy at B? No, there's no spring involved. So that goes to 0. So we're left with U initial at A is equal to kinetic energy at B. And then by formula, we know that this is equal to mgh at A, and that's equal to 1/2 mvb squared, so the velocity of B squared. And, well, what do we really want to solve for is the question. Let's take a look at what values we know. We know what mass is, we know what g is, we know what height is at A, because we're given that to be 5 meters. We have mass on this side, we do not have velocity on the right-hand side, so maybe velocity would be a logical thing to solve for. So let's do that. We have a mass on both sides, so those cancel. And we're left with 2gha is equal to vb squared. So vb is equal to the square root of 2gha. And if you've been sticking around long enough and seen some of the previous videos, this equation should be feeling very familiar. We've seen the square root of 2gh many, many times. So if you see this while you're solving a question, perhaps that's a good sign. This is very, very common to see this. Okay, well, we have values for g and ha, so let's substitute them in. 9.8 times 5. Let me just pause a moment to go over why h is equal to 5. Remember that h is the vertical distance from where we are at, in this case at point A, to the h equals 0 line. The h equals 0 line is basically given to us by this flat surface. That's where we decided to define h equals 0. And we were given that the vertical distance from A to B, which is what we're looking at, is 5 meters. So that's where that 5 meter comes from. And if we do this multiplication and square root, we get this is equal to approximately 9.9 meters per second. Okay? So now let's consider the journey from B to C. And then we'll consider C onwards. But let's just see what happens from B to C. Okay. So let's use conservation of energy once again. So E initial plus work non-conservative is equal to E final. K E initial plus U initial plus U spring initial plus work non-conservative equals K E final plus U final plus u spring final. And again, what we're going to do is just think about, are any of these quantities 0? Okay, so let's just put the subscripts on the left and right side. So at B, we're on the left side, we're at B, and on the right side, we're at C. Okay, dealing with the left side first. Is there kinetic energy at B? Yes, we just found the velocity at B. It's not equal to 0, so certainly there's kinetic energy there. Is there potential energy there? No. Why? Because we're at the h equals 0 line. So there's no potential energy there. And yeah. What about spring potential energy? Also no. There's no spring involved on the object at B. So don't need to worry about that. That also goes to 0. I should probably be saying these go to 0. Non-conservative forces. Are there any present from B to C? Yes, that's kind of why we broke it up into A, B, and C, because from B to C there is this rough patch here that has friction. So we need this term still. Okay, let's look at C. Is there kinetic energy? Maybe. It's very possible that the block stops somewhere in between here. So we're not entirely sure, so let's keep that term there for now. Is there potential energy at C? No, because we're at h equals 0 once again, so that goes to 0. And then, is there spring potential energy at C? And the answer to that is actually no. We're just reaching C, right? This is the point right after we get off of this friction part, and we haven't yet encountered the spring. Even if the spring was like, the picture is pretty bad, but the spring should reach this friction part right here, and we're just considering the moment it leaves this, and like the moment right before it hits the spring. I'm having a tough time speaking today. So even though it may seem like, okay, there's a spring involved at C, no, we're just considering the moment it reaches there. So there's no contact with the spring, really. And even if there was, the spring starts in equilibrium position, so that x value would be equal to 0, so this goes to 0 as well. Beautiful. So simplified, we have KE initial B plus work non-conservative equals KE final at C. All right, let's use our equations for this. 1/2 mvb squared plus f sub f times d times cosine of theta equals 1/2 mvc squared. All right, I'm going to sort of expand all of this in one go, and either you can believe me or you can't. And I'll explain why we did this in just a moment. Let me just change this. All right, I'll give a very brief understanding of why we went from here to here. And if you're still confused about why that's the case, we did something very similar right here. You'll notice that this is exactly the same thing. The reason for this is friction. We know that's equal to mu times f sub n. If we draw the free body diagram from B to C, the only we have Fn pointing upwards, we have Fg pointing downwards, we have friction pointing this way. So if we take the sum of the forces in the y direction, we get Fn minus Fg is equal to 0 because we're not accelerating in that direction. So we have Fn equals Fg, so Fn equals mg. So this Ff is mu times f sub n, so that's mu times mg. D is the distance that this force is being applied for, so that goes from B to C, and we denoted that as x, so that's just that. Theta is the angle between the direction of motion and the force vector, so the direction of motion is to the right, friction opposes that direction of motion, so that's to the left. That angle is 180 degrees, so cosine of 180 degrees is -1. So that's how we did that simplification there. Okay? And so what quantity should we try to solve for here? We have m, we have VB, we solve for that right here. So we're good there. We're given mu, we said we have m, we have g, we have x, that's given to us. We have m, we do not have vc, so perhaps we should try to solve for v sub c. Okay, so let's just simplify this a little bit further. We get 1/2 mvb squared. This is minus mu mgx equals 1/2 mvc squared. We see that there's a mass in all of these terms, so that can cancel. We'll multiply by 2 on both sides to get rid of some of these halves. So we get rid of this, we get rid of this, and this term multiplies by 2. And then we'll just take the square root of both sides. Square root. And all of that will give us v sub c is equal to the square root of vb squared minus 2 mu gx. And, well, we have all of these quantities, so we can substitute in here. VB, we said, was 9.9 meters per second. So this is 9.9 squared. Minus 2 mu is 0.25. That was given to us. G is 9.8. X is 1, also given to us. So if we compute this out, we get 9.65 meters per second. So right now it seems kind of willy-nilly that we're just like solving for velocities all of the time, but like we kind of want to figure out how does the spring compress, but like we haven't really been doing that. We've just been finding velocities, but the progress that we're making is that now we know what happens to the block as it goes down to here. So we're finally reaching the spring, and pretty much all we know is the velocity of the block at that point C. So hopefully that'll give us some insight into how it interacts with the spring, right? We couldn't just figure out how far that spring compresses without knowing anything about the block at C. So we had to figure out how does the block change from here to here? How does it change from here to here? Now we'll figure out how it interacts with the spring. Okay. I'm just taking a look at my notes as to what we're doing. Okay. So now we'll consider what happens from C to the end. Actually, let's just try to copy this picture. There, copy, and then we'll go here, paste. Okay, good. So we'll go from C to the end. And again, we'll use conservation of energy. Same equation we're used to at this point. K initial plus U initial plus US initial plus work non-conservative equals K E final plus U final plus USF. And again, we have to consider what are the forces that are 0, which ones are not 0. And the good thing is, well, we're starting at C, so let me put our subscripts C on the left side, and then here I'll just leave it as F, because it's just some final position. Well, if this left-hand side has to do with C, we kind of just already analyzed what are the energies at C, and we said that, okay, only kinetic energy is there, the other two go to 0, so let's just say the same thing here. This goes to 0, this goes to 0. And you can check that to be sure. But then we have to see, are there any non-conservative forces? And, well, at C, we don't have that frictioned path anymore. Sorry, patch. I keep on saying path. We don't have that frictioned patch. So friction's not present. We're on a frictionless surface, and there's no other non-conservative forces. So that also goes to 0. So then what does the final position look like? Well, let's try to draw it. We have like the surface here, and the block's going to keep on sliding, until it reaches some point here where the spring is like compressed a lot and it momentarily stops. And that's the point that we're really curious about, right? How much does the spring compress? We're curious about what is this distance. So this is sort of the final position. So with that in mind, does the block have kinetic energy at that point? Hopefully you're saying no. If it did, then the spring would compress even further, but we're curious about the point where it stopped compressing. So the block has momentarily stopped, so that goes to 0 because there's no velocity. Is there potential energy? No, because we're at h equals 0. Is there spring potential energy? Yes, because the spring is no longer in equilibrium position. Up here we're in equilibrium position, but now the block has squashed the spring, so there's so much energy stored up in here that it wants to push the block backwards, and in fact that's what's going to happen. After the block has compressed the spring, this block will go flying that way. But we're not concerned about what happens afterwards. We just know that there is some energy held up in there, so this term is not 0. Okay, so this simplifies things. We have KE initial at C equals USF. And we have equations for this. 1/2 MVC squared equals 1/2 KX squared. And now finally we're getting somewhere, because this x is really what we're trying to solve for. That is the displacement from equilibrium, the compression distance. That is this mysterious question mark quantity that we're trying to solve for. So let's try to solve for x here. We see that there's a half on both sides, so those cancel. We get x squared equals mvc squared over k. So that means x is equal to the square root of mvc squared over k. And right now you're just hoping that we have all of these quantities so we can be done with this question. Do we have m? Yes. Do we have k? Yeah, we were given that. Do we have v sub c? And you might be like, oh no, we don't have that. But in fact we do, because we solved for that. From b to c, we said the velocity at c is equal to 9.65. So certainly we can solve for this. This is the square root of what's the mass of the block? 2 kilograms. 2 times 9.65 quantity squared. All of this divided by k, which is 10. That's going to be equal to 4.31 meters, and that's our answer. So, such a simple looking problem, and we were able to determine how far will the spring compress. It's going to compress 4.3231 meters, which is actually a lot. Those who are unfamiliar with the metric system, that's about like 13 feet, something like that. That's a lot. So this is a massive spring, actually. And the reason for that is that the block is being dropped from a height of 5 meters. So 9.9 meters per second is actually really fast. These numbers seem kind of meaningless to those who are unfamiliar with the metric system. 9.9 meters per second is quite fast. So that's why it compresses so much. Fantastic. We got one more question. I'm feeling a little tired, but let's push through it. We'll do that and then maybe just chat afterwards if we want to. So it's this one. It's a little bit annoying, but all good. Let me just get a drink of water first. Can read through it in the meantime. Alright, so we have these blocks that are connected by a spring, which is kind of weird. I think we've seen some things where blocks are connected with a string, but this is a spring, which is slightly different. And we're given the spring constant, and the spring has a negligible mass, so that's good. System is being pulled to the right across a horizontal frictionless surface by a force of 4 newtons. And both blocks are experiencing equal constant acceleration. And then we want to find the force that the spring exerts on the 2 kilogram block. Okay. So, how are we going to do this? Well, let's take a look at the block, the 2 kilogram block. So that's just there. What are the forces being applied to it? Well, we have gravity pointing downwards. We have the normal force pointing upwards, and we have the spring force, which is pulling it to the right. That's about it. So, if we sum the forces in the x direction, that's equal to mass times acceleration in the x direction. So Fs is equal to mass times acceleration in the x direction. We're trying to solve for this F sub s. We have mass, we just need this acceleration term. And the way we can get that acceleration term is by looking at the system as a whole. So instead of these 2 separate blocks connected by this spring, just consider this to be one supermassive blob which is being pulled by this 4 Newton force. So when we consider considering the system as a whole, if we take the sum of the forces, that should be equal to mass times acceleration, just by Newton's laws. Okay, so in particular, we'll look in the x direction. And so really, the only force in the x direction is this 4 Newton force on this entire system. This spring force, yeah, sure, there's a force pointing this way, but there's also a force pointing this way, right? The spring is like trying to pull these together, so those cancel out. So we're left with this 4 Newton force is equal to the mass of the system, which is 2 plus 8, times acceleration, which gives us that the system is accelerating at a speed of 4 divided by 10, which is equal to 0.4 meters per second squared. So using that, we can now solve for F sub s. So then F sub s is equal to max, and we're looking at only the 2 kilogram block in this context, so mass is 2, acceleration is 0.4, we do that multiplication, we get 0.8 newtons. Alright, so that's part A. Part B is asking us the extension of the spring, so we want to find delta x. Well, we know that F sub s is equal to 0.8 newtons, and we know F sub s is equal to k times delta x. So that just means delta x is equal to F sub s divided by k, and we have both of these quantities. F sub s is 0.8, k is, what is k? 80. And if we do this division, we get 0.01 meters. So these two questions, kind of simple, just reminding us to use Newton's laws and Hooke's law. Then we get into this situation here, and we'll do this, I guess, qualitatively. I won't write everything else out. Okay, so the system is now pulled to the left as shown below, with both blocks again experiencing equal constant acceleration. Is the magnitude of the acceleration greater than, less than, or the same as before? Well, how did we find acceleration? We said the force is equal to the mass of the system times acceleration. So the force is still 4 newtons, right? It's still 4. And the mass of the system is still 2 plus 8. We have 2, we have 8, the system 10 kilograms. So this acceleration calculation is going to be exactly the same. So this is the same. Okay? Is the amount the spring has stretched greater than, less than, or the same as before? Alright, so let's take a look at the free body diagram for block B in this case, since that's the one that's like further away. we have Fg pointing downwards, we have Fn pointing upwards, and now we have the spring force to the left, since the thing is going to the left. And well, if we sum the forces in the x direction, we get that's equal to m times the acceleration in the x direction, which tells us F sub s is equal to max. F sub s we said is k delta x. That's equal to max. And we're trying to solve for delta x. So delta x is equal to max over k. So this is a very similar process to what we did here. Just, I guess, slightly different views here. It's in terms of F sub s, but we said F sub s is equal to max. So if we just make that substitution in here, we get that that equation would be identical to this. So now we'll just plug in the numbers. Mass now is 8. Acceleration is the same as before, which is 0.4. And k is equal to 80, same as before. And we can see that this will actually be greater than this. I believe that this comes out to what? 0.04. So that's greater than this. So answer D is greater. And lastly, part E, in a new situation, the blocks and spring are moving together at a constant speed of 0.5 meters per second to the left. Block A then hits and sticks to a wall. Calculate the maximum compression of the spring. Okay. Do we want to do this? Yeah, let's do this. Okay. So this is quite the interesting situation. So we have this block here. This is A, and then it's connected to a spring. This is B, and it's moving to the left. And block A hits the wall. So our initial thing that we're going to consider is the moment it hits the wall. But then when it hits the wall initially, block A is going to stay where it is, right? It's not going to move. But block B is still going to move because it hasn't really hit anything. The spring is in equilibrium. So we imagine it would compress the spring. So we'll compress the spring, and B will be here, and then the system will be at a different position. So initially, we're going to say this is the moment the system hits wall. And then finally is the moment B stops and spring is maximally compressed, right? And the reason we chose this to be the final position that we're looking at is basically we're trying to find this maximum compression of the spring, and that occurs when, B has compressed it as much as possible, which is when B will momentarily stop before it goes that way. So with this setup, it seems like conservation of energy is the way to go. So we have E initial plus work non-conservative equals E final. So we have K E initial plus U initial plus U spring initial plus work non-conservative equals K E final plus U final plus US final. And now hopefully some of these terms will go to 0. So initially, we should really be looking at block B the entire time, because here this is the moment the system hits the wall, so block A has 0 velocity here, and at the end it also has 0 velocity. So block A doesn't change, so we should really be looking at block B. So focus on block B. So, does B have kinetic energy the moment the system hits the wall? Yeah, we said that B is going to continue moving this way, so there is some velocity, so it has kinetic energy. Is there potential energy? Well, we should probably define H equals 0. So we'll just say that somewhere here is h equals 0, and I didn't draw it level, but since it's the same situation, that's also h equals 0. So with that definition, there is no potential energy initially. Is there spring potential energy initially? No, because initially, we're looking at the moment the system hits the wall, so this spring is still in equilibrium at that moment. Later on, it won't be in equilibrium, but at that moment, it's in equilibrium, so there's no potential energy in the spring. Are there any non-conservative forces? Hopefully it's frictionless, the surface. Please say it's frictionless. Yes, it's frictionless. Beautiful. And there's no other non-conservative forces. Okay, so now let's consider the final position here. Does the block have kinetic energy? No, because we said B will momentarily stop there, so it has no velocity. So this goes to 0. Is there potential energy? No, because we're at h equals 0. Is there spring potential energy? Yes, because the spring has been compressed. So we have this. So we have Ke initial equals USF, 1/2 mv squared equals 1/2 K delta x squared. This delta x and x, like this could be 1/2 kx squared. That's perfectly fine. I'm using delta x just to signify that it's measuring a change in displacement. But even if we just left it as x, that's fine because we defined x to be that change in displacement from equilibrium. So this is just notation, whichever you choose to use is perfectly fine, as long as you understand what it's doing. The 1/2s cancel, and we're trying to solve for delta x. So we get mv squared equals k delta x squared. So that means delta x squared equals mv squared over k. So that tells us delta x is the square root of mv squared over k. And we have quantities for all of these. We have mass is 8 kilograms, I believe, right? That is the mass of B, which we're given here. The velocity of B, do we have that? Let's see, are we given that in the question? Yes, we are. It's 0.5 meters per second to the left, so the system is moving with that speed 0.5 meters per second, but that also means that this block is moving at that speed. So we're going to multiply this by 0.5, and the spring constant K we're given to be 80. We do this computation, and we get delta x equals 0.16 meters. That's our answer. So that is this question. It's kind of annoying when you see this, like, 2 blocks connected by a spring. But the key to these questions is, again, considering it as a system, what's going on when the blocks are, considered to be as one grouping, and then break it apart individually. If it helps, draw a free body diagram for each of these blocks. Take all of the sums in all of the directions, whatever helps. Give yourself as many equations as possible, and then use that to attack your question. I've sort of simplified the process in that I just gave you like which free body diagram we should be looking at, but if you didn't know this, well then take the free body diagram of A, and if that doesn't help you, then that's okay, but maybe it does help you. You'll just have more information, which is good. So that's going to conclude our lesson on springs today.